This question is from the GATE Physics paper 2020. This is a numerical answer type question having 2 marks. The topic of the question is electromagnetic theory. The question is a sinusoidal voltage of the form V as a function of time t equals to V0 times cosine of omega t is applied across a parallel plate capacitor placed in a vacuum. Ignoring the edge effects, the induced EMF within the region between capacitor plates can be expressed as a power series in omega. The lowest non-vanishing exponent in omega is. So let us see how to solve this problem. It is given that a sinusoidal voltage of the form V as a function of time t equals to V0 times cos omega t is applied across a parallel plate capacitor. Let the separation between capacitor plates be small d. So it is shown in the schematics that two plates of the capacitors are separated by the small distance small d, and we have considered a small circular loop at the center having radius small r, and the area of the loop is given by the shaded region here. So we will calculate the induced EMF along this circular loop. So the electric field between the plates of the capacitor is E equals to the applied voltage along the capacitor plates, that is V as a function of small t, divided by the separation of the capacitor plates, that is small d. So the time varying electric field between the capacitor plates is given by E as a function of small t equals to V0 divided by d times cos omega t. We know that according to the Maxwell's theory of electromagnetic induction, if a time varying electric field exists in a region, then there will be a time varying magnetic field associated with that time varying electric field, and that is given by the Maxwell's equation. Curl of the magnetic field B equals to mu naught times epsilon naught times daily del T, where mu naught is the magnetic permeability in the vacuum, epsilon naught is the electrical permittivity in the vacuum, and E vector is the electric field vector that is coming here due to the applied time varying voltage across the capacitor plate. Now we will take the surface integral both sides of this equation. So it is given by surface integral of the curl of B vector equals to mu naught epsilon naught times surface integral of daily del T. Here the surface is considered by the surface area of the small loop of radius smaller that has been shown in the schematic in the first slide. Now we can convert this surface integral into the closed path integral. So that is given by closed path integral, line integral of the B vector equals to mu naught times epsilon naught times surface integral of daily del T times the ds vector. So here the line integral part will give B times 2 pi r. Here 2 pi r is the circumference of the small loop having radius smaller that we have considered in the first slide, and that is equal to mu naught times epsilon naught times this daily del T, that will give minus v naught omega divided by small d times sine omega t times the surface area of the circular loop, that is pi r square. So from this we can find the associated magnetic field, that is B equals to minus R times mu naught times epsilon naught times V naught divided by 2 small d times omega times sine omega t. So this is the expression for the time varying magnetic field associated with the time varying electric field between the capacitor plate. Now, according to the Faraday's law of electromagnetic induction, we know that if a time varying magnetic flux exists in a region, then there will be a induced electromotive force, and that is given by induced EMF E equals to minus d phi dt. Here phi is the time varying magnetic flux in the region. So the induced EMF E equals to minus d dt of the magnetic flux that is given by magnetic field B as a function of time times the area of the region. So A is the area within the region between the capacitor plates here. Now area is constant here, so it can come out from the derivative. So E equals to minus A times d dt of the magnetic field. Now we have calculated the magnetic field associated with the applied voltage across the capacitor in the last slide. So this d dt of B will give here as E equals to A times, that is the area, times R mu naught epsilon naught V naught divided by 2t times omega square cos omega t. Now the terms in the parentheses are independent of omega, so we will not write it again and again. We will consider the omega dependent part here. Now we will expand this cos omega t in the power series. So this expression will give E equals to this term times omega square times the power series of the cosine of omega t, that is 1 minus omega t whole square by 2 factorial plus omega t to the power 4 by 4 factorial plus so on. Now we will multiply omega square with this series, so this will give omega square minus omega to the power 4 t square divided by 2 factorial plus omega to the power 6 times t to the power 4 by 4 factorial plus so on. So we can see the lowest non-vanishing exponent of omega is 2. Therefore, the lowest non-vanishing exponent in omega from this expression is coming out to be 2 here. According to our solution, the lowest non-vanishing exponent in omega is 2.